Hello and welcome back to today's video. In this video, we're finally going to talk about angles between vectors. I've repeatedly talked about how the scalar product will enable us to measure angles. And now we're finally at the point in our lecture where we can see how this will work. So this section is titled Angle. And actually, the idea is pretty simple. We've seen how the scalar product is related to orthogonality and to orthogonal projections, and we make use of that fact right now. So here's a picture that you will probably remember from school. Let's draw a two-dimensional coordinate system here, R2, and we draw a vector in that system. We call that vector x. And we'll assume that the length of the vector is 1. So the vector x here, that is on the unit circle, right? So here's 1, here's 1. The length of x is 1. Now if we look at the orthogonal projections of x onto the two coordinate axes, here's the x1 axis, here's the x2 axis, then the projection onto the x1 axis is given by this here. So this is the first projection. The projection onto the x2 axis is this here. So that's the second one. Now, if we denote this angle here between the x1 axis and x by alpha, then you can see that this projection onto the x1 axis, the length of this orange bar here, that is equal to the cosine of alpha. While the green one here, that projection, the length of the green line is equal to the sine of alpha. So if we have a vector that is in that first orthant here with positive values for the x1 and x2 axis, then we can simply say the following. The cosine of alpha is given as the length of the projection of x onto the x1 axis. Or if x is not normalized, then of course we have to normalize first before projecting. So we compute the projection onto the x1 axis, and that is the span of the vector 1, 0. We project x divided by its norm. And then the cosine is not that projection, but the length of that projection, right? So this here is equal to the cosine. And of course, we need x not equal to 0. And we also need x to be in the first orthant for this to work more precisely. But regarding the signs, so if x is not in the first orthant, but in the second, third, or fourth orthant, then of course the sign of the scalar product will flip, and also the sign of the cosine might flip. And it turns out those signs are in sync, so we can just do without the absolute value here, and then everything will be fine. And of course the same would be true for the sine, so we could also use that one. Usually we use the cosine, but of course that works for the sine in a similar way. So that is the projection onto the span of 0, 1 of x divided by its norm. And again, to get the sine, of course that's only a real value, not a vector, so you'd have to take the norm of that one. In general, things are pretty similar. So let's say we have a setup where we have again a vector x, like this. Of arbitrary length. And then we have another vector y, maybe like this here. Oops. And we can compute the projection of x onto y, of course. And to do that, what we do is we have a look at this line here. So we need a right angle here. And then this line here, this is the projection. All right, so what we get here is the projection of x onto the space spanned by y. And again, we can have a look at the angle here. So that angle here is called alpha. And then, of course, the length of this projection will again reflect the cosine. So the length of this projection is exactly equal to the cosine of alpha times the length of the vector x itself. Yeah. Again, we'd have to normalize that to get the cosine. So if we don't normalize, we just multiply the result with the norm, and that's again correct. Okay, so what we have here is the length of x times the cosine of alpha is equal to the length of the projection onto that space y of x, and we need the norm here to get the length. And well, that projection, we know how to compute the projection, so that is the same thing as the scalar product of x with the normed version of y times that vector. And now if we do the computations here, we can solve that for cosine alpha. And what we get is then the scalar product of x and y divided by the norms of x and y. And more precisely, of course, this first formula here, this only holds for the positive orthant, so where the x1 and x2 x's are positive. Or in other words, for degrees alpha that are between 0 and pi over 2. And we'd have to have an absolute value here for that to be true. Now, if you look at the possible signs of that scalar product and of the corresponding cosine of alpha for angles that are larger than pi over 2 or less than 0, then we'll find out that those signs correspond. So this general formula here still holds, even if you have angles outside of that range. So this includes angles outside of that range from 0 to pi over 2. So what that gives us in general is the following remark. If we have two vectors, then the angle between those two is given by this expression here. So for two vectors, x, y, in R to the n, the angle, let's call it angle alpha, between x and y is given as cosine of alpha is equal to the scalar product of x and y divided by the norms of those two. And note that this expression here, this scalar product here, divided by the norms, that is actually in the interval from -1 to 1, as it should of course be. If that's a cosine, it needs to be between -1 and 1. And we can be sure that this is between -1 and 1 by Cauchy-Schwarz inequality. So that's one of the places where Cauchy-Schwarz plays an important role. So this is the formula for computing the angle between two vectors based on orthogonal projections. And now you finally know how this scalar product is actually related to angles. So basically it's the cosine of an angle if the two vectors are normalized. Otherwise, you of course need to multiply or divide by their respective lengths to get that. So this concludes our investigation into angles. And in the following videos, we're going to have a look at another application of orthogonal projections. And I hope I'll see you then.